morning, Calculus 1. I'm going to do another derivative here. I'm in section 3.1, trying to do derivative the long way with the definition that we've learned. And this is kind of a difficult one. And then I got a couple other ideas, and that should kind of round out 3.1 here. So let's get busy here. There's the good old definition of a derivative. By the way, what is a derivative? It's a transformation of the original function to a new function that tells me what? The slope of the tangent line. So we transform the original function into this new function, f prime of x, and it tells me the slope of the tangent line to the original function. I've said that several times, but it's always worth repeating. Anyway, I want to try it for this function, and that's going to take some work. Here I go. The derivative is the limit as delta x goes to 0. And then I need f of x plus delta x. That means I take the function and I plug in x plus delta x for that x. So then I have minus 3 squared in the denominator there. That's f of x plus delta x minus f of x, which is just the function itself. So my numerator is full of these fractions, and then it's all over delta x. So that's kind of a mess. That means you got to kind of get a common denominator in your numerator. So I'm going to work here. I might end up over there. So here we go. Oops. Sorry, that's okay. I don't need to really rewrite that. Here we go. Equals. So common denominator means that's going to be wow. The common denominator is going to have x. It's going to have that, x plus delta x minus 3 squared, and it's going to have that, x minus 3 squared. Wow, and so the new numerator is going to have, and it's all over delta x, remember? The new numerator then is going to have, let's see, what does he need to get a common denominator? Oh, he needs the x minus 3 squared. Minus, that's that minus sign, and then what does he need? His new numerator will be this guy, x plus delta x minus 3 squared. Wow, that's a challenge. And by the way, oh, and there's the limit as delta x goes to 0. You know, this is a little messy here, but what I need to do is expand this numerator. That's going to take a lot of work. I got to FOIL it all out. FOILing, that's not too bad, but FOILing, that's going to take some work. And then I'm probably going to do this. I've got a delta x over 1 is what I like to think of it. I'm probably going to flip it up and end up multiplying by a 1 over delta x. This is going to flip up. All right, so let's start. Let's see what we got. The limit as delta x goes to 0. Okay, so I'm foiling this x minus 3 squared. That's x squared minus 6x plus 9. Like I said, that was easy. Minus... I'm foiling this. Boy, I don't even know how to foil that. I got to write it out probably. Let's write it out. X plus delta x minus 3 times x plus delta x minus 3. A little scrap paper work here. X times x squared. There's an x delta x. Remember, when you multiply an x times a delta x, it's like two different variables. That's all that you can't combine it really. X times that negative 3. So I just multiplied x times everybody. Let's multiply delta x. Okay, there's a delta x times x. There's a delta x squared. There's a negative 3 delta x. Wow. Let's multiply the negative 3 times. Negative 3x. Negative 3 delta x and a plus 9. If I gather my like terms together, here I'm moving back over here. I've got an x squared. I think I got 2 of those. Plus 2x delta x. I got a negative 6x, I see. Yeah, I see a negative 6x. I see a negative 6 delta x. I see a plus 9 and a plus delta x squared. I don't know what order. You might have wrote that in some different order. I wrote it in that order. Wow. And then it's got this denominator. Good Lord. X plus delta x minus 3 squared times x minus 3 squared. Wow. And then remember it was all over delta x, but I'm flipping that up over and it's 1 over delta x, so that means I've got this multiplied delta x in this denominator. Now, guess what? I bet you that numerator cleans up big time. I need that space, so I'm going to erase my scrap work I did there. And I'm going to cancel several things in this numerator. When I distribute this negative sign, which I'm going to do in my head, that x squared is going to cancel with that x squared. It's going to be a negative x squared. That negative 6x, and there will be a positive 6x. They'll cancel. There's a positive 9. This negative sign will make that a negative 9. That'll cancel. So that negative sign still needs to distribute. I get a negative 2x delta x, a positive 6 delta x, and a negative delta x squared. All over this crazy denominator. Don't forget you're taking the limit as delta x goes to 0. Here comes this denominator. A lot of writing. I'm sorry, a lot of writing. But remember, you love math. Don't forget, you love math. You love algebra. That's what helps you get through this. Can you tell me what's next? Tell me. You know, you still have, if I try to do this limit as delta x goes to 0, I still get a 0 over 0. Maybe you can see that. So here we are, we factor out that delta x. Everybody that didn't have a delta x canceled. That's pretty typical. And now I'm factoring out this delta x, and it'll cancel with this delta x. Then I'll be good to do the limit. So factoring out the delta x in the numerator, you know, if you don't mind, can I just, let me just do that right above here. I'm factoring out a delta x in that numerator. That leaves me with a negative 2x plus 6 minus delta x. So that numerator just became that numerator. That delta x cancels with that delta x. Let me rewrite what I got here. Let me rewrite it for you. Now I have negative 2x plus 6 minus delta x in that numerator. And I got this denominator still. X plus delta x minus 3 squared and x minus 3 squared. All right, I think I'm finally ready to do the limit. As delta x goes to 0, I get, that goes to 0. I get a negative 2x plus 6. That goes to 0. Oh, this little delta x goes to 0. So I have an x minus 3 squared and another x minus 3 squared. I do not want to FOIL that out, or what I do want to join them together. That's an x minus 3 to the 4th. Ta-da! That's the derivative. That was kind of a complicated derivative. This function has that derivative. You know, the truth is it's not quite simplified yet. Let's do a little bit more work. If I factor out a negative 2 out of that numerator, I'm left with x minus 3, I think. And that's, yeah, that's correct. And then that one of those x minus 3's can cancel. So I can cancel one of those x minus 3's, which leaves me 3 of them in the denominator. So actually, the derivative is, here we are, we're done. The derivative for this function is a negative 2 over x minus 3 squared. Cubed. Wow, that was a long one, you guys. Hey, that was a good one. I want to point out a couple things. I haven't mentioned this yet. The derivative sometimes is undefined or does not exist. We kind of use those words in there. Look at this derivative. Now this derivative is undefined when you can't divide by 0 in mathematics. So it's undefined when x is 3. The derivative is undefined when x is 3. So there's no slope there. There's no slope of the tangent line there. Or the slope is undefined. Something's weird. But we could have predicted that. If we go back to the original function is undefined at x equals 3. Maybe we should know what that is. It's a discontinuity, and it's a vertical asymptote is what it is. So at x equals 3, the original function had a bad place, a discontinuity, and therefore the derivative also was undefined. What we call that then, when the derivative is undefined, is we call that a the function is non-differentiable. The derivative doesn't exist. The function is non-differentiable at that point. So I'm going to go back, I'm going to get rid of all this work, and I'm just going to go back and mention that this function, you say the function, not the derivative, but it's based on the derivative being undefined, but then you say the function is non-differentiable at x equals 3. Again, it was kind of an obvious one. I want to talk more about non-differentiability. There's some that aren't so obvious. But it always happens when the derivative is undefined. That's what you're looking for. And then you can go back and say the function is non-differentiable. I think this one was obvious. Look, anytime the function's undefined, its derivative will also be undefined. So when we saw that bad place 3, we knew that was coming. I guess there could have been more bad places. But, you know, so I like to find where it's non-differentiable. I think your homework and will ask you, where is it differentiable? So, you know, I hope that you can, if it's non-differentiable at 3, then where is it differentiable? Everywhere else, and we give it an interval on the x-axis, so we say negative infinity up to 3, comma, or union, or 3 to infinity. I mean, that's the whole real number line, except I left out 3. So, you know, it's easier to identify where it's non-differentiable. They often want you to tell them the answer, where is it differentiable? So, everywhere else. So this is a good topic. I'm gonna get rid of this stuff here, sorry. Should tell you to hit pause. So I'm going to just stick with this non-differentiable topic. I'm going to leave this function for a second. I'm going to tell you functions are non-differentiable at these places. You ready? There's 4 places. Sharp points. Sharp points. So if the function has a sharp point, it'll show up in the derivative as being undefined. It's probably not undefined in the original function. A sharp point could look like this. Look, that point exists. That in the original function, that point exists. It's not undefined. But it will show up as undefined in the derivative, and therefore you'll know that the derivative is undefined, and therefore the function is non-differentiable. The function is non-differentiable at that point. And you could try to explain why. I mean, the derivative is going to be undefined, but you can't have a tangent line at that sharp point. If I try to draw a tangent line, it doesn't seem to really, it doesn't work. This limit doesn't exist. I'll tell you another one. An endpoint. We ran into that on a square root function. Look, we found the slope of the tangent line on different places on a square root function, but if you get to this endpoint right here, you can't really have a tangent line at that point. At the endpoint, the derivative fails to exist, the derivative is undefined, and the function is called non-differentiable. So sharp points, endpoints, this is an interesting one. A vertical tangent line. A vertical tangent line. By the way, these places all exist on the function. I mean, these places are defined in the function. They'll be undefined in the derivative. Watch this picture. A vertical tangent line looks like this. Actually, that's kind of a famous cube root function. There's a place, there's a place right there where it becomes vertical. So the slope is fine. I mean, there's a tangent line there. There's a tangent line there, but it's vertical. And if you remember from algebra, a vertical line has a slope that's undefined. So the function's non-differentiable when you have a vertical tangent line. You do have a tangent line, though, which is better than those other 2 cases. But because it's vertical, its slope is undefined. One more. And this was the obvious one. This was this one. This one was discontinuity. So if you have a discontinuity, then you got a hole, you got an asymptote. There's no, if it's a discontinuity, it's not defined in the original function, and therefore there's no tangent line there. A hole, an asymptote, a break of some sort. I mean, you can't, if you have a discontinuity, I mean, there you go. This time it's defined, but you can't have a tangent line there. So the function is non-differentiable at these four places. You can look for them visually, graphically, or what they show up as undefined places in the derivative. They show up as undefined places in the derivative. Okay, good. Listen, that's the last topic for 3.1, and that's the last topic for my first exam. Chapter 2, limits, and Chapter 3, 3.1, this limit, this famous limit, this couple ideas here at the end of 3.1, and that ends the topics for the first exam. So, so I'm excited to get into 3.2, 3.3, 3.4 for the next exam. I want to teach you how to do derivatives the shortcut way. We're going to quit doing limits for a while. You'll love it. So I can't wait to teach you that stuff. All right, thanks for listening. Thanks for working hard.